Okay, so now we're going to talk about how to deal with collisions. And the first strategy we're going to look at is one known as linear probing. So linear probing, the idea is that when we realize there's a collision in the table, we don't give up. What we do is we just look at the very next entry in the table or the next index in the table to see if it's free. And if it's free, we use it to hold the item we want to insert. It's called linear because you just increment the index to find another place to store the data. So for example, if I want to store 433 and we are still using our simple mod 10 hash function, when I mod 433 by 10, I get the third index, but the third index is occupied by this number, 59,343. So I can't put it there. That's a collision. So what I do is I just take that index 3, I increment it by 1 to 4, and I look to see if it's available, and turns out it is, so I store 433 there. Then, if we were to carry this on, let's say I want to put 1003 in my table, that again hashes to index 3, it's occupied, index 4 is occupied, index 5 is occupied, but index 6 was available, and so we store 1003 there. So linear probing is just this idea that if the first position in the hash table is being used, you increment until you find a free entry and you store the data there. So a question we would then need to ask is how far to probe? How far do we increment the index to find an empty entry? This is very important because it's critical that we keep insertion O1, right? We want inserting into our set to be fast. And in the extreme case, let's say we checked the whole table. If we check the whole table for a place to insert, then insertion would become big O of n, where n is the size of our table array. And that would clearly be undesirable. That would be a very slow worst case insertion time. What we want to do is check a small but constant number of entries beyond the hash index. And let's call this small constant number the probe distance. And we will not exceed the probe distance. We can set that probe distance to be whatever we want, but it needs to be a constant. And probably to keep things fast, it should be relatively small. Okay, so that gives us some code that looks like this. And now this is a much smarter way to handle insertion. So just like before, we calculate the index. And now I'm going to have this other variable called buckets probed that lets me know how many places I've considered to insert the value. While buckets probed is less than probe distance, I can keep considering locations. Okay, so the first location I consider is the main index. And so if the table index is available, actually, I'll talk about what this less than 0 means in just a second. If the index is valid, then I'm going to put the data there. Oh, I'm sorry, actually, right. We're assuming an uninitialized entry is negative. So if it's negative, I can put the data there and return true. Otherwise, I increment the index by 1. Now I have to do this index plus 1 modulo size because it could be my index is at the very end of the hash table array. And if I'm at the last index in the hash table array, what I want to do is wrap back around to the start. And so by moduloing against the size, it just guarantees that I stay inside the bounds of the array. So I increment by 1 and go back around. And I can keep doing this as long as buckets probed is less than the probe distance. Okay, and then if after looking through that probe distance worth of entries, I still don't find a location to put the item, then I am going to return false to indicate that insertion failed. Now, that's how insertion works. How does searching work? Well, we're going to check for a match at the index first, right? So again, if I'm looking for 433 and I'm mod 10, I'm going to check position 3 in the hash table first to see if it matches, but it doesn't match. So then if I don't find it, I need to check across the entire probe distance. Let's say the probe distance is 3 in this case, then, or I guess this would be 4. So I'm going to check 0, 1, 2, and 3. I'm going to check these 3 locations. Fortunately, I'm going to find it on the very next location. I'm going to find a match at 433. But this could be inefficient for hash tables with very few collisions. Like if this is my hash table and I'm looking for 1014, you know, I don't find it at the index where it should be, there's nothing else here within the probe distance. So actually, I'm not going to find it at all. And if I have a very sparsely populated table, most of the time, I'm not going to find it outside of its actual index. So the problem with linear probing is that it adds cost for hash tables that are sparse and have few collisions already. So we'd like to fix this. We'd like to avoid extra searching within the probe distance if we can. And so this is actually pretty easy to fix. All we need to do is recognize kind of a basic idea. If we've never put data in a hash table index, then that means linear probing has never inserted something there, which means we don't need to look any further. We can stop the search immediately. So we're going to classify all the entries in our hash table array into 3 categories. The first one is that it's valid. It's currently holding valid data. The second category is that it's always been empty. It's been empty since the start. The entry has never held data. If we're doing a search and we find an entry that's never held data, then that means linear probing has never needed to go past that point to do an insertion. And so we can immediately stop the linear probing search. Likewise, if we find empty after removal, then that means this location used to hold data, which means probing could have gone past it to insert data, so we do need to keep looking. Okay, but it currently doesn't have any data at the moment, so the match can't be at that location. So these 3 categories allow us to do a search more efficiently. So the idea is that now when I hash 433 into the table and I don't get a match at position 3, if the very next location is empty since start, then that means I never did an insertion at 3 that failed. Because if I had, I would have put it at 4. So as soon as I see empty since start, I can stop searching, and I don't need to consider the whole probe distance. So this is going to make our solution more efficient. Okay, so now our search function looks like this. While the table index does not equal empty since start, and while the buckets probed is less than the probe distance, then we look to see if it has the data. If either of these becomes false, we're going to break out of the loop, right? So as soon as I find an entry in the table that's empty since start, I know the data can't be there, and we're just going to give up. Likewise, when I do removal now, I can do the same thing while table index does not equal empty since start, because if I get to an empty since start, then I didn't find the data. I can be confident of that. And now instead of setting the entry to -1 to indicate there's no data there, I'm going to set it to empty after removal to indicate that there used to be data in this position, but now there's not data in that position. All the rest of this code remains the same as it was before. Okay, so in summary, linear probing utilizes empty adjacent entries in the hash table to resolve collisions. Entries within a probe distance can be used, but we must keep probe distance a small constant to guarantee O1 efficiency when we do insert, remove, and find. We label buckets as valid, empty since start, or empty since removal to make the search and removal process more efficient.